autotrophy were not anymore functional. Then we made a control conditions with a normal amount of nutrients and an enriched condition where the algae were heavily fed in nitrogen. So according to the hypothesis, we were expecting that here, with no autotrophy, the animal host would feed a lot. And here, with this condition, with a lot of autotrophy, the animal would feed nothing, would take nothing from the plankton. Okay? And so we followed heterotrophy with two different techniques. The usual technique, the classical technique, which is plankton grazing, and one technique which is the isotope labeling. And we cultivate corals under two conditions, 25 and 30 degrees Celsius. 25 is the normal temperature for corals, and 30 degrees is a high temperature inducing bleaching. So this is the two techniques. So the classic method is just classic. So we put a coral nubbin into a small cage like this. We put plankton in the water, a small stirring of the water, and we just count how much plankton cells is decreased in the seawater. And the decrease in plankton means that it has been eaten by the coral colony. So, for example, we start with 10,000 plankton cells, and after 2 or 3 hours, we measure 5,000 plankton cells. So we know that the coral has eaten 5,000 plankton cells. With the isotope technique, it consists in labeling the plankton with C13 here and N15. And to label the plankton, we have to first label the algae with bicarbonate C13 and nitrate N15. Once the algae are labeled, we feed the plankton or the artemia with the algae. They become labeled, and then we follow the labeling in the corals. So completely two different techniques. And this one shows really the assimilation of nutrients, what remains in the coral tissue after a while. What we get, so here we have the grazing, so we have here the number of plankton prey ingested in our small chamber, and here we have the 3 different conditions of autotrophy. So the depleted one, where the algae are not functioning, and the enriched one, where the algae gives a lot of nutrients to the corals under 2 different temperatures. And what you see is no real difference in grazing rates with the usual technique. So the first wrong conclusion that we can say, I mean it's wrong because I know that it's wrong, is that the autotrophic level or the seawater temperature does not change the heterotrophic capacity of the coral. So from here we would say, okay, whatever comes from the algae, the coral host, the coral always takes the same amount of nutrients, the same amount of plankton from the water. So now I try to simplify. This is just the assimilation of nitrogen with the use of isotopes. So we measure how much N15 goes inside the coral tissue, or in the algae, or in the coral host, under the 3 different autotrophic conditions. And I just represented here the 30 degrees Celsius. It's just. And what we can see is in this condition, the corals which are lacking food from algae also lose their capacity to feed on plankton. And this is a really high decrease in the assimilation of nitrogen. I don't show you all the results, but temperature is also a big effect, because all the assimilation in the 3 conditions, the assimilation of nitrogen also decreased under high temperature. So as you see, we don't get the same results with isotopes. So with isotopes, we see the effect of autotrophy. And in fact, we end up to a conclusion that is completely different from the one that was stated at the beginning. At the beginning, we said, okay, if the corals don't have anything from autotrophy, they will shift on heterotrophy, on the grazing by the host, on plankton. And this is not what we see here. When the corals cannot get anything from autotrophy, they lose their capacity to assimilate nitrogen from the plankton. I don't know if it's clear because it's the two fluxes. And it's completely a different conclusion that we end up. So finally, we have this, that when we have global warming affecting the corals, already the global warming decreased the inorganic nutrients outside because, as you all know, there is a thermocline in the surface waters, and so the nutrients are not coming up again from the deep waters. So usually we have shallow waters depleted in nutrients. And as I told you, there is also a bleaching, so the corals lose their algae. So in fact, they lose completely their autotrophic acquisition of nutrients because they don't have any more algae, they don't have any more inorganic nutrients. But now we know that the coral host cannot rely on heterotrophy. In fact, it was a wrong hypothesis. So the coral host, we know that it also loses its heterotrophic capacity, and as a conclusion, corals die from starvation. So when there is no autotrophy, no input from the algae of nutrients, there can be an input from plankton and from the host. And this was a new conclusion compared to the previous one, who thought that the corals can shift from one feeding mode to another one. So this is the first example, was how we can use isotopes to follow these interactions. I have a second example with the isotopes. This was for Ulysse, because he worked a lot on these diazotropes. So the bacterial, the microbial component of the corals. So we know that the diazotropes, they transform the nitrogen into ammonium, and then this ammonium can be used by the other components of the corals. And the diazotropes, they can be in seawater, in the coral mucus, in the coral tissue, in the coral skeleton. And the question up now is to know if corals assimilate the nitrogen fixed by the microbes, and in which condition they can assimilate this nitrogen. So this is Ulysses worked a lot on this. So here again we have two techniques. The classic technique that is to use to enclose a coral into a beaker like this, and to estimate the activity of the nitrogenase, which is the enzyme transforming N2 into ammonium, by putting acetylene and looking at the transformation of acetylene into ethylene. This technique is a proxy for the nitrogenase activity, except that it's a gas that stays in as a gas. So we just measure the acetylene at the beginning and then the ethylene at the end of an incubation. Except that this technique gives no information whether the nitrogen is assimilated by the coral and where the nitrogen is assimilated. Because corals, even if you filter the water, even if there is nothing in the water, due to their mucus layer, the corals can enrich the water in diazotropes, in bacteria, I would say. So at the end of an incubation of several hours, you will have all bacteria, all the seawater enriched with bacteria due to the mucus release. And even if you measure some ethylene production, so some nitrogen fixation by the diazotropes, you don't know where this if the nitrogen remains in seawater or goes into the coral. So by using isotopes, again, instead of putting a gas, we put a gas, but the N15 that is labeled with the isotope N15. This N15 is transformed into ammonium N15, and this we can follow directly in the seawater or in the coral tissue. So we tried this technique 2-3 years ago, and this is a work from Vanessa Betnar's recent work. We went to the Red Sea. We went to the Red Sea. We used the common coral here of the Red Sea, which is Stylophora. We incubate the Stylophora into closed chamber by adding N15, and we took 3 different corals. One coral from shallow water, 5 meters depth, one coral from deep water, 50 meters depth, and one coral that has been bleached, so which has lost its dinoflagellate, its algae. And we did some incubation with N15, and we look where the N15 ends up, in fact, if it ends in the seawater particles, in the coral tissue, or in the algal symbiotes. And this is what we got. So in gray, we have just what is in the seawater, and in blue and green, it's what is in the coral, either in the dinoflagellates, in the algae, or in the coral tissue. And what you can see is in shallow waters, everything is in the water, in the particles of the water, but nothing is in the coral tissue. So the corals are not, even if there is N2 fixation, the corals, they don't get this nitrogen, at least in the Red Sea and when we did the experiment. But when the coral is bleached, so has lost its zooxanthellae, its algae, and cannot acquire inorganic nutrients from the water anymore, then it relies a bit more, by 30%, on the diazotrophs, on its bacteria, on the food coming from the bacteria. And in the deep corals, it's even more. It's 90% of the total nitrogen that has been fixed by the bacteria that goes into the coral tissue. So then we thought, okay, we don't know in these conditions, we have now two questions, whether the diazotrophs were more active in the coral tissue in these two situations, or more abundant, or whether the corals ingest more of the seawater diazotrophs, because the corals are releasing the diazotrophs in the seawater, and maybe they can retake these diazotrophs, these particles, through heterotrophy.